The universe has a size limit for stars, and the reason it exists will completely change how you see space. Betelgeuse is 1,000 times larger than our Sun, but it is not large because it is powerful. It is large because it is dying.
Stars that grow too massive destroy themselves. Their own light becomes stronger than gravity and tears them apart from within.
Watch the full documentary on Noxar Flux, the complete story of what the universe allows and what it absolutely does not.
This is our Sun, a relatively quiet star of average size, and yet it dwarfs our entire world.
Our Sun has a diameter 109 times larger than Earth and contains nearly all the mass in our solar system. But compared to the galactic supergiants, our Sun is nothing more than a small, unassuming neighborhood star. Betelgeuse is one of the largest known stars, with a diameter of approximately 1.4 billion kilometers. For context, our Sun has a diameter of 1.4 million kilometers, making Betelgeuse roughly 1,000 times larger. These are sizes the human mind struggles to truly comprehend, yet they raise an even more profound question.
Is Betelgeuse truly the limit of how large a star can grow, or is something even more extreme possible?
To answer that, we first need to understand how any star grows this large at all, and it begins with one force. That force is gravity, the same invisible pull that holds you to the ground right now as you watch this. In space, enormous clouds of gas and dust slowly attract each other, pulling inward under their own gravity. The more material falls inward, the greater the pressure inside becomes, and the hotter the core grows. Eventually, the heat becomes so extreme that nuclear fusion ignites in the core, and a new star is born. What was once an invisible cloud of gas and dust has become a radiant, burning star shining into the void.
Now something remarkable happens. The fire inside pushes outward while gravity pulls inward, and they balance perfectly.
This equilibrium is exactly how our Sun has burned for nearly 5 billion years. A perfect, unbroken cosmic balance.
But Betelgeuse was never like our Sun. From the very beginning, it was 15 to 20 times more massive.
And in the universe of stars, a simple rule governs everything. The more massive the star, the faster it burns. Imagine two campfires, one small and steady, the other enormous and blazing. The larger one always burns out first. Our Sun still has roughly 5 billion years of fuel remaining, while Betelgeuse has nearly exhausted its supply. Betelgeuse has burned through its fuel in just a few million years, an incredibly short life on a cosmic scale. When a massive star runs out of core fuel, something seemingly contradictory happens deep inside its structure.
The core contracts and heats up further, but the outer layers of the star react in the opposite direction entirely.
Those outer layers begin expanding outward, pushing further and further until the star becomes enormous. It is like a campfire that flares up wildly one last time before finally going out, growing enormous in the process. Betelgeuse is not a young star in its prime. It is an ancient dying star, expanded in its very final stages of life. If placed where our Sun sits, Betelgeuse would stretch all the way out to the orbit of Jupiter. Mercury, Venus, Earth, Mars, all four would be swallowed completely, lost deep within a single dying star. Betelgeuse is so large precisely because it is consuming itself, burning through its last reserves in one final blaze. Astronomers have confirmed that Betelgeuse will end in a colossal supernova explosion within the next 100,000 years. That explosion will be so bright, it will be visible from Earth even in full daylight for several months.
For a brief period, Betelgeuse will shine nearly as bright as the half moon, visible to every person on Earth.
But this raises a fascinating question. If Betelgeuse is large because it is dying, how large can a young star become? Is there any limit at all to how massive a star can grow during its prime, its most powerful active phase? The answer leads us to some of the most extreme objects ever discovered in the entire observable universe.
And yes, there is a limit, and this limit even has a name that scientists have studied for over a century. To understand it, we need to return to that equilibrium inside a star: fire pushing out, gravity pulling in.
A star is stable as long as those two forces remain equal, but with the most massive stars, a serious problem arises. The heavier a star becomes, the hotter and brighter it burns, and brightness itself becomes the danger.
At a certain mass, a star becomes so incredibly bright that its own light begins pushing its outer gas layers away.
Light actually has force. When a photon collides with a gas particle, it delivers a tiny push, just like a billiard ball. With an extremely massive star, so many photons are released every second that their combined push becomes immense. The gas is literally pushed outward and away from the star, out into open space, by the force of its own radiation.
This radiation pressure is so real that scientists have designed spacecraft propelled by sunlight alone, called solar sails. With our sun, gravity easily wins, but with a star hundreds of times more massive, radiation pressure takes over. From this point, the star can no longer accumulate new mass. Anything drawn toward it is immediately blown back out.
The star is constantly fighting against itself. Its own energy has become its greatest limitation and its prison. This is the Eddington limit, the point at which a star becomes so bright it prevents itself from growing any larger.
Theoretically, this limit sits at around 150 to 300 solar masses, beyond which a star simply cannot grow further.
Such stars do exist. One known example sits in a small neighboring galaxy and is 200 to 300 times our sun's mass. If our sun were placed next to this star, it would appear as nothing more than a tiny spark beside a bonfire.
However, stars this extreme are incredibly rare and burn through their fuel in just a few million years total. They live intensely, burn fast, and die young, the most dramatic and brief lives in the entire stellar universe.
A star exceeding this limit simply could not exist stably. It would begin tearing itself apart the instant it formed. The radiation would be so extreme it would blow away the outer layers before the star could even take solid form. It would not function as a star at all, but rather as a gigantic, self-destructing explosion with no stable core.
However, there is one fascinating exception to this rule, and it lies far back in the earliest history of the universe. Shortly after the Big Bang, conditions everywhere were radically different from anything we observe in the present universe. Under those extreme early conditions, the very first stars in existence could have been several thousand solar masses. We have never observed them directly, and they vanished long ago, leaving only theoretical evidence of their existence. But their existence suggests that the rules governing stars were not always the same as they are in our universe today. In the present universe, the limit is clear. No star can permanently grow beyond 150 to 300 solar masses.
It becomes too bright for its own existence. Its light destroys it from within before it can ever grow any further.
It is a strange and beautiful idea that a star's limit comes not from outside, but from within its own brilliant nature. When a star like our sun exhausts its fuel, it expands into a red giant, then contracts into a small white dwarf.
A white dwarf is roughly the size of Earth, slowly cooling over billions of years, a quiet and undramatic final chapter.
But with the galactic giants, the stars of hundreds of solar masses, there is absolutely no quiet final phase at all. When a star of this extreme mass dies, what happens ranks among the most powerful events in the entire universe.
The core collapses in literal seconds, and the outer layers collide with it and are ejected outward with unimaginable force.
The resulting supernova explosion is so bright that for a brief moment it outshines entire galaxies of billions of stars. If such an explosion occurred in our cosmic neighborhood, it would shine brighter than the full moon for months.
The
most massive stars trigger something even more extreme, a hypernova, releasing concentrated radiation in twin beams. These gamma-ray bursts are the most energetic phenomenon the universe produces, concentrated beams of pure lethal radiation. A single gamma-ray burst releases more energy in seconds than our sun produces across its entire 10 billion-year life. And what remains at the very center after this explosion is something that defines the ultimate limits of physics itself. The core collapses so completely under gravity that it creates a region from which not even light itself can escape. A black hole, the most extreme object in the universe, and the final legacy of the most massive stars that ever existed. These stars begin with light powerful enough to blow away matter, and they end with gravity so strong light cannot escape. From one extreme to the other, these giant stars push physics to its absolute limits and then transform those limits entirely. Now I want to hear from you. Could our sun ever become a giant like Betelgeuse? Drop your answer in the comments right now. Subscribe to Noxar Flux so you never miss a story. New space documentaries are coming every single week, only on this channel.